Okay, welcome to another video on shear force and bending moment diagrams, and today we're going to be looking at uniformly distributed loads, which are essentially the ones that have the shape of a rectangular load on top of your structure. So in this case, what we're going to do is, first of all, we know that we need to find the equivalent resultant force. So the magnitude of that force is going to be equal to the total area of this rectangle, which is going to be 10 by 5. So the resultant force is going to be 50 kilonewtons. And then the next thing is, we know that it is going to be acting right in the middle of this cross section. So that's where the center of the area is. So that's going to be located at 2.5 meters from the center. So one thing we could do is we can draw a free body diagram over here. And we're going to have a force acting right in the middle. So that's going to be 50 kilonewtons. And it is going to be located at 2.5 meters from each side. Now the next thing we know is we're going to have two reaction forces. On the left hand side we have a hinge support, which means we're going to have both vertical and horizontal reaction forces. But this one over here, let's call it RAX, is going to be 0, and we know that because there are no external horizontal forces acting on this system. Then we have RAY and RBY. Now the next thing we know is, well, this is simply loaded beam. The magnitude of the force of this distributed load is right in the middle. This is completely symmetrical about that center axis. So that means that we could pretty much just assume that the forces are going to be equal. So if this is equal to that, and the sum of those forces is equal to 50, then each of these needs to be 25 kilonewtons. So without actually having to go through the process of deriving those equations, we already know this is going to be the result, because we have done problems like this ones quite a lot so far. Now the next thing we want to do is we want to draw the shear force bending moment diagram. So the shear force diagram is going to look like this. That's going to be in kilonewtons, and then the distance x in meters. So we're going to have the force acting over here, so that's going to be at 2.5 meters, and then at 5 we should see the diagram coming back to 0. So in this case what's going to happen is quite interesting, because remember that when we're actually looking at this shape, we're no longer talking about a point load, even though that we treat it as a point load for the purpose of calculating the reaction forces. But rather, since this is a constant distributed load, the actual shape of this diagram is going to be a straight line with some gradient. So essentially, we could say that the shear force is the integral of the distributed load with respect to x. So if this is a constant, then the integral of a constant is a linear equation, which means that we're going to have a linear equation over here. Now I could go through the process of deriving that, but I can actually do this directly over here by saying, okay, we start off by going up by 25 kilonewtons. And now we notice, okay, so the load is pointing downwards, which means that we're going to go down like that. And since the middle, or essentially the force crosses, the resultant force is right in the middle, then this line has to cross this. Because remember, we're going to go down. So along the total 5 meters, we're going to go down by 50 kilonewtons. So we're going to subtract 50 from this. So we're going to end up somewhere over here. So that means that our shear force diagram is going to look like this. So probably not drawing it very well, but you get the idea. This should be a straight line going downwards like that. Okay, so now that means we have a positive area over here, and then a negative area over here. And we notice that this is a symmetric kind of diagram, so this has, well, in this case it is antisymmetric, but you get the idea because this is a symmetric loading scenario. Similarly, if I wanted to derive this using the simple method of just plugging it into the integral, then the way we can do this is as follows. We're going to have some integral over here, so the integral of the constant 10 dx, and then we integrate that, that gives us 10x plus c. And then the next thing is going to be, well, if we look at this equation, what is going to be the constant C? We need to find out what that is. And usually that constant is related to the reaction force that is right at the beginning of the section. So if we choose this point over here to be x equals 0, then C is going to be the shear force at point 0. So shear force at point 0 is going to be equal to the reaction at AY, which is equal to 25. So in this case, the shear force equation is going to be 10x plus 25. Okay, so that's essentially it. But now, one thing that we need to notice is that, hang on a minute, this is actually going down. And it makes sense because if you look at your distributed load, this is actually pushing the beam down. So that means that we should actually make this negative over here. So the equation should actually be minus 10x plus 25. And that makes sense because if you plug 0 into here, you get 25. And then if you plug x equals 5, you have minus 50 plus 25. So you end up over here. So that's the correct equation you should actually have in this case. Now for the bending moment diagram, what we're going to do is very simple. So we're going to draw it over here. So let's have bending moment in kilonewtons times meters. And then here we have x meters. Now the next thing we're going to do is we're going to have the origin over here. We could do the same technique that we used before, so we could actually find the area of this triangle and then just basically plot it over there. But let's think about this for a second. The bending moment is by definition the integral of the shear force. Alright, so if we already know this equation over here, then that means that we can actually know what the equation of the bending moment is going to be. So in this case, we just integrate that function. So that becomes minus 5x squared, because remember this, we're going to bring a 2 down here, so divide by 2, that becomes minus 5x squared, plus 25x, plus some constant of the bending moment. But in this case, we notice that if we look at the structure, the bending moment reaction at the very initial point, at the origin, is essentially non-existent. There's no reaction there, which means that this is going to be 0. So the constant Cm would be 0. So now if we look at this equation over here, we plug this in here. So we know that we're going to start over here. This is going to be a concave down parabola. Alright, so we know that this is going to be like that. But essentially we know that since this area is positive, we should actually start going up like this. So at 2.5, we know that we should have the same area over here. So if we look at this, well, we have, let's see what that area is. It is going to be half of 25 times 2.5. So let's calculate that very quickly. So that's going to be 31.25 kilonewtons meters. And notice that if we actually plug in 2.5 into this equation over here, we would actually get the exact same answer. So we can either use the graphical method just by calculating the area, or we can use the equation itself and just plug in the values directly. Now if we plug in x equals 5, then we should get back to 0 because this area is negative. So remember, we're going to go down now. And we know, well, this is a negative area, so if we subtract this from that, which is already 31.25, then we're going to get back to the origin. And we know that should be the case because this is a concave down parabola, so it has to come down again. And if we plug in x equals 5 into this equation, then we should get the exact same answer. And this is going to be your bending moment diagram. Now, hopefully, using this method, you now understand a little bit better what we mean by having a distributed load. And in fact, this method of integrating the distributed load is quite general. So we could have any shape of distributed load. We integrate that directly, and that's going to give us the shear force. And then, if you integrate the shear force, you get the bending moment. Now, the one thing to notice is that the constant of integration is going to be related to the shear force and bending moment acting at that initial point. So if you choose the left-hand side here to be x equals 0, then whatever internal reactions you have there, for example, reaction force gives you the shear force, and if you have a bending moment, that gives you the constant that corresponds to the bending moment, and so on. So that's essentially how we deal with those. And in the next video, we're going to do a very similar example, but we're going to extend it to more complicated cases.